To compute the ERP, we averaged the EEG data across many trials. This is a nice plot, but how confident are we that the values extend significantly above or below the baseline level, in this case the value 0? To address this, let's include confidence bounds in our plot of the ERP. To do so, we'll make use of a powerful theorem in statistics, the central limit theorem. Briefly, this theorem tells us that the mean of a sufficiently large number of independent random variables, each of which is well behaved, will be approximately normally distributed. Remember how we compute the ERP. It's the mean of the EEG data across trials computed at each moment in time. Let's make the assumption that the trials are independent. This means that what happens in one trial does not depend on what happens in any other trial. Let's also make the reasonable assumption that our EEG data are well behaved. This means that the mean or the variance is not going to blow up and go off to infinity at any time during our observation. With these assumptions, we satisfy the requirements of the central limit theorem. We conclude that the ERP at each moment in time is approximately normally distributed. This conclusion is useful because the normal distribution, sometimes called the bell curve or Gaussian distribution, has many convenient properties. First, we can specify a normal distribution with only two parameters, its mean and its standard deviation. Second, 95% of values from a normal distribution lie within approximately 2 standard deviations of the mean. So, to construct the ERP with 95% confidence intervals, we need to compute, at each moment in time, the mean of the EEG data as well as its standard deviation across trials.